In this lecture, we're going to discuss interpretation and interpreter optimization. So to this point, we have studied how high-level languages are represented when they are transferred over a network to a target machine for execution, or when we convert our source code to an intermediate representation that's portable so that we can execute that everywhere. Typically, this is done using a bytecode format. As we talked in the past, Java Virtual Machine uses a bytecode format. Its instructions are typed. Their opcodes are 1 byte in width. That means there's 255 possible, 253 are currently used. The remaining part of the instruction is 0 or more values that we're going to be operated on, and these are the operands. These are variable length instructions, and much of the operand information can be left off because we're using a virtual operand stack in order to perform our operations. This keeps the code really compact. MSIL is the Microsoft Intermediate Language for the .NET runtime. It's very similar to the Java bytecode. However, there are opcodes that are 2 bytes in length, which gives us 64K possible instructions in this language. Finally, Python has a bytecode format. It has 113 opcodes. 42 of them have arguments, 71 do not, and these are untyped opcodes. So both MSIL and the JVM have typed instructions, and Python does not. So, for example, if you're going to perform an add in Python, you don't know until actual execution time, when you can interrogate your operands, what the operation is. Say, for example, an add, until you can look at the operands at runtime, you don't know if you're performing a concatenation of strings or an addition of 2 integers. All of these languages, these bytecode languages, use an operand stack for 1 or more of their operands, excuse me. And the goal of the runtime system is to translate this intermediate representation of your program to native code at runtime so that your program can be executed on the target machine. So there's a couple ways to do translation. We can do it via interpretation, or by compiling the program to native code. And what this lecture is about is the interpretation. Interpretation is line-by-line execution of the program. This is where every single instruction, bytecode instruction in the program, as it is executed, is decoded, parsed really, to figure out what its operand is and what its what its opcode is and what its operands are. And then that instruction operation is implemented in another language. So again, what we're going to do is we're going to take each instruction one at a time, decode it, figure out what it's doing, and implement it using another language. Typically C or some lower level language, but you can do it in other languages as well. Notice that if I'm executing in a loop and I encounter the same instruction twice, I do all the work again. I read the instruction, I decode it, I parse it, I figure out its operands and its opcode, and I implement the operation using a different language. The sort of code bodies, the functions that implement each opcode, that is each operation in a language, is called a handler. And you may have a language instruction in the bytecode that needs to be broken down into multiple operations, and then each of those operations has a handler. So, for example, if we have the Java bytecode I_add, we encounter it for the first time, we're going to read it from its location in memory, where the code block for the method is, and we're going to decode it so that we take out the opcode to determine that it is an I_add. At the same time, we're able to use that information to invoke a handler that is a function written in another language like C. we call the function, the iadd handler, we call that function, and that function implements the iadd semantics. That is, it pops the top of stack of, this is the operand stack now, the top of the operand stack is popped into a local variable x. This is repeated. The top of the operand stack is popped and put into local variable y. We then add those two values in x and y and put them in z, and then we push the value z onto the top of the operand stack. Notice that in this case, the interpreter, the runtime implementation, maintains an operand stack in memory that these handlers, this particular handler and its implementation, use to push and pop the values so that the next instruction can continue on using the functionality, the semantics of the stack machine. Of course, there's other data structures in addition to this operand stack in memory at runtime. We talked about a few of them in previous lectures. The main one that you'll remember is the statics table, where all things global and all things static are held in the runtime. The benefits of interpretation are many. It's really great for fast prototyping of new languages and instructions. So say, for example, you wanted to take the Python language and add some new instructions to it. You could easily extend the Python interpreter with this new functionality to investigate the utility of the advances you're making. Sometimes an interpreter is used to define the operational semantics of a language. For example, Ruby, there is no specification for the Ruby language. There's just an implementation of the language in an interpreter that is used as the reference for that language definition. Next, and I think the most important reason that interpretation is used today is because it's portable. Notice if you write the interpreter itself in a high-level language, that is, you implement all the handlers in a high-level language, you simply have to recompile that code to run on different architectures. In a compiler, what you're doing is you're going to actually generate the native code, that is, the binary code for a particular architecture for the code bodies in one of these languages like Java. So the compiler is necessarily non-portable because it has a code generator for a particular architecture. An interpreter, on the other hand, since it's written in a high-level language, higher level than binary, a language like C, all we have to do is simply recompile the runtime system, the interpreter itself, for a particular architecture, and now the programs that it's interpreting can run anywhere that the interpreter is. It's really easy to port interpreter to different architectures. Interpretation is easy to reason about. It's just a simpler way of executing a program. So in some cases, it can be easier to debug in terms of a runtime system than a compiler that's generating binary code and putting it in memory. There's a smaller footprint, a much smaller footprint, because you're not generating native code. Again, the bytecode of these languages like Java, .NET, and Python are really compact because we use bytecode. But when we generate native code for that, it's much larger, 7, 9, 10, 15 times larger in some cases. And so since we have to keep that around in the runtime, that increases the size of the footprint if we're compiling. Notice interpretation doesn't keep code around at all. It simply calls a handler for each of the instructions. Now, the handlers themselves take up space, but again, we're not generating code for the program itself. We're simply executing it within the handler. So sometimes the footprint of the runtime system will be smaller. Next, interpreting code is much faster than JIT compiling in terms of the translation process. We only have to interpret one instruction before making progress in the execution, whereas compiling requires that we translate more than one instruction, and so it's just going to be a little bit slower for the translation process. But overall, the executed code is probably going to be faster if you compile, so there's just a trade-off there. It's easy to add tools to interpreters, which is another benefit. The downside of interpretation is that the code, when it actually executes, is slow and much slower than if you compile to native code. So the idea with compilation is you compile a method once and you take a pause, a hit to the performance during that time while you're waiting for the method to be compiled for the first time. But once you've compiled it and put it into memory, you can just execute it natively after that. So overall, compilation, if the program executes for more than just a few seconds, is going to be faster. Notice that when we interpret a program and we encounter instruction that we had interpreted already, say we're in a loop, you do all that work again. With compilers, you do the work once, and then you can take advantage of it and amortize the cost of compilation later. So even the fastest interpreters produce code that's or execution that is 5 to 10 times slower than native executable code, but it could be much, much worse than this, 100x for some programs, for some languages. All bytecode languages can be executed using interpretation, and the actual implementation of the interpreter is typically referred to as a decode and dispatch loop, or a switch dispatch interpretation. So let's take a look at what that looks like. This is the interpreter from CPython, the most popular runtime system for the Python 2.7 language. This is a big for loop, notice, and within that for loop, it's really an infinite loop. The first thing we do is we read the next instruction in a program, and we're going to decode that instruction and extract its opcode. Once we have its opcode, we then check if there's some arguments. Based on the opcode, we know which opcodes have arguments, which opcodes don't, so then we can decode those. And finally, we use the opcode in a big switch statement for all of the possible opcodes to find the handler. We use a case statement for the particular handler, and that allows us to jump to the handler or invoke the handler as a function. And so the first thing you want to observe is, okay, this is going to be happening for every single instruction. When we're done with the handler, we're going to break, and that's going to cause us to come out of the switch and to traverse the loop again for the next instruction. The first thing you want to try to do is reduce the overhead of the interpretation loop. That's what we're going to be talking about today. There's lots of ways of doing that. But the first one you should be thinking about is, if I'm executing this code over and over for every single instruction that my program executes, what are some things I could do to make this faster? Well, the first thing to do is observe that on every single instruction, we're going to check if the opcode has arguments. As I said before, just about half of the opcodes have arguments, the other half do not. So we may want to move this check into the handlers themselves so that we don't have to perform it for the half of the opcodes that have no arguments, because for that, it's just a waste. There's much more that we can do, though. But first, let's dig deeper as to why things are slow in this loop, this decode and dispatch process. Notice on the left we have some bytecode. If we were able to execute this bytecode using natively, so if we could directly execute this bytecode, the control would flow just within the bytecode itself during execution. Now there'll be jumps around this bytecode, but you'd stay within the bytecode program itself. If you are executing it with interpretation, a decode and dispatch loop, the bytecode now sits in memory and is just like a big array of data. And so the dispatch loop is going to read from that piece of memory, that piece of data, and to get the next instruction. It's then going to decode that instruction and figure out what handler to jump to, and then it's going to invoke a handler for that opcode. If you notice this process, not only do we have the branches that may occur naturally in the bytecode, but we have a ton more branches that are going to be occurring because of the dispatch and decode loop. So first thing to remember from your architecture class is that Branches can be conditional and unconditional. Conditional branches are like if, for example, if then else statements in your program, and this is where you have a branch target and a fall through. You can either jump based on a condition, or you're going to just fall through to the next instruction based on that condition. Next, branches can be direct or indirect when they're actually implemented in the hardware. Direct branches are where we can encode the target of the branch in the instruction itself. Now, we still don't know if we're going to take that branch, but we know where we're going to jump once we decode that instruction in the hardware. So that's called a direct branch. Again, the address to which we are jumping is encoded in the native instruction itself. Indirect branches are where we have to do a lookup to figure out where we're jumping to. Typically here in the native ISA, the native code, the binary instruction, in the instruction is encoded a register address. And so this instruction, in order to make a jump, has to go and get the value that's in that register, do a lookup to see what value is in that register, and then jump to that instruction. So there's additional overhead in indirect jumps. Anytime you do a call or you return from a function, these are indirect jumps. So again, more review from our architecture classes of the past. Most of our modern architectures execute using a pipeline. In this case, we have a very simple pipeline. Most pipelines today in modern architectures are very, very deep. 19, 20 stages deep. This one is only 4. And so these stages are the fetch. This is where we read the instruction, get the instruction into the processor. Next phase is the decode phase, DEC, and it's where we're going to parse the instruction to see what the operands and operations are. Now, again, this isn't the hardware, so we're doing a similar thing to what the interpreter was doing, but now we're doing it in hardware to execute it on the physical machine. Okay, so the third stage of this pipeline is execute. This is where we actually do the computation. And the very last stage is the write back stage, which is where we write our result to whatever our destination locations are. So in this example, we're just going to be executing some instructions. I want to show you what happens when you hit a branch. So instruction 2, I2, is our conditional branch instruction. And if you remember, every time that there's a branch, if it's a conditional branch, we have a jump edge. That is, that the condition is such that we're going to take the branch. We're going to jump across the branch. So that's called the jump edge. A conditional branch, if it doesn't satisfy the condition, will just fall through to the next instruction. So on every conditional branch, the next instruction is unknown until we're able to determine the condition, the outcome of the condition. Okay, similar for unconditional branches, or some which are also called jumps, as in basic block 3, BB3, where I have a go to BB4. Even though we know exactly where we're going, we have to decode this instruction in the hardware before we can discover where we're going so that we can make the jump. So for unconditional branches, we just have a jump edge. Now, again, as I mentioned in the previous slide, these targets of a branch or a jump could be encoded in the instruction, and that would be a direct branch or a direct jump. And if they're encoded in registers, then we have to go look up that register, and that's called an indirect branch. Okay, so back to our example on the right. At time 1, an instruction is fetched and brought into the processor, and at time 2, that instruction number 1 is going to move to the decode phase. At the same time, instruction number 2 gets fetched, and this is our branch. Now notice we don't know what the target of the branch, what the next instruction is at this point. It could be, if we're talking about the last instruction in BB2 on the left, it could be that we take the fall through edge to BB3, or it could be that we take the jump edge to BB4. We don't know what instruction is next. So what we have to do is guess. And there's hardware support for this guessing. This is called branch prediction. And so we're going to guess that instruction 3 is next. That is, that the branch is going to fall through. Now, there's nothing here that says that I3 is the fall through. I'm just making that up at this point. So we're going to guess that we're going to take the fall through edge for this branch. So we load I3, which is the first instruction in BB3. And at that point, I2 is now in the decode phase. As soon as so we're going to proceed on. So now we proceed on, and we fetch I3, and in the next time step, we're going to fetch I4. Now I2 has made its way all the way to the execution phase of the pipeline. This is where we actually know what the correct next instruction is. At this point, if we were right and I3 was the next instruction, we would be golden. We wouldn't have any problems. We'd just proceed on. Our guess would have been right. However, in this case, we were wrong, and the jump edge was taken for I2. But we have brought in I3 and I4 incorrectly. So what we have to do now is flush the pipeline. This produces bubbles in the pipeline. This means we have to get rid of everything that happened after I2. And so I2 is going to move to the write back phase, and only after that phase can we start the pipeline fetch on the correct instruction, IA. And that bubble proceeds through the pipeline, and that just reduces the throughput of our processor, slowing down the overall program. So branches are really hard on performance of our programs because of this reason. So when we're talking about decode and dispatch loops and interpreters, not only do we have a lot more branches introduced on top of what the program already has, all of these branches, direct and indirect, are difficult to predict. The switch case we have no idea about. We have to load the operand, we have to load the opcode and evaluate it and figure out what its target is, put its target into a register, and use the switch case to jump to the handler. This is a register indirect branch. Very hard to predict because it really depends on what the next instruction is. The interpreter routines, every time we call a handler, there's a overhead of an indirect jump to the call. Sometimes we can do a direct jump if we know exactly where we're jumping to, but still it's difficult to predict address because we don't know what handler we're going to execute. Again, it's dependent on what the program is doing. Same thing for the return. We don't know where we're returning back to. That's going to be an indirect branch. And in the very end, when we have to loop back around to the interpreter loop, we have to do a conditional test and branch, which is also hard to predict, although easier to predict than the others. Because typically we're going to stay in the loop rather than exit out, because we're only going to exit out when the program is done. Okay, so our paper today is about how we can speed up this process, and we're going to focus on these branches because a lot of time is spent in these branches. Let's just see how much time that is happening there. Okay, no, let's first just look at the optimizations that we can do. So here on our left is the switch case. I just kind of compacted it some, but basically the idea is in the normal decode and dispatch, we're going to have an infinite loop. We're going to, inside that loop, we're going to read the opcode. We're going to use the opcode to switch into a case for a particular handler. That handler is going to be a function invocation to implement that instruction, that opcode. We're going to return back to the case from which we called that handler. We're going to then break out of the switch case. We're going to read the next instruction, and then we're going to loop around back to the while to get as long as we have more instructions, we'll continue to loop. So the first thing we can do to make this faster is get rid of the outer branch. The idea here is, why don't we just put in the test for the and the get for the next instruction inside each of the handlers, and I'll explain this better in the next slide. The next thing we can do is get rid of those function calls. Every time we call a function in return, we have one, if not two, indirect jumps to handle. So what we'll do here is we'll put all of the handler code at a known location in memory, and then put their addresses of those locations into a table, and therefore if we can index it by the opcode. So we get an opcode, we're going to look that opcode up in a table to get an address. We're just going to jump using goto to that table, the address that's in that table, and thereby we're going to avoid the function call in return. And then finally we can take this one step further and inline the handlers into one long interpreter code body. So this is called indirect threading, and on the right is what it looks like. So what I'm going to do, I'm going to get things started. I have bootstrap at the top, and I'm going to get the first instruction, check that it's not null. Assuming it's not, we're going to get its opcode, and we're going to use that opcode to index into a table called handlers that is going to return an address, and we're going to use the goto instruction to jump directly to that handler. Excuse me. Once we've done that, we're going to jump to the instruction, the address that's in that the handler returns, and an example is in the op-a label down below. So this is an implementation of a certain opcode. The first thing we're going to do is we're going to get the next instruction. First thing we're going to do is going to implement the opcode that we just for this instruction. When we're done, we've now inlined the process of looking up the next instruction. We get the next instruction, check for if it's null, get its opcode, use that opcode to get the next address. And so what we're doing is we're just linking a bunch of handlers together into one huge program of linked handlers. And notice for every single operation, we're going to need to duplicate those 5 instructions after each opcode implementation, where we get the next instruction, check for whether it's null, get its opcode, use the opcode to index into the handlers table, and jump to the address at that location in the table. All of that is going to be in every single handler now, and that way we can link all of our handlers together, and this is called indirect threading. This improves the prediction for the handler targets. If we're in a loop and opcodes occur in the same sequence, then the branch predictor has a better chance of getting that right. Say, for example, you have the add instruction, which is always, or typically, is push a value onto the operand stack, push a value onto the operand stack, pop those off and add them, and then push a value onto the operand stack that is the result of the add. So you have push, push, add, pop. Okay, so if every add is like that, then you're going to see push, push, add, pop repeatedly. So if a push comes after a push, then branch predictor the next time will see that relationship and be able to predict that branch better. If an add always comes after a push, then again, there could be a pattern there that the branch predictor can take advantage of. It's much better than completely random, which is what we had before with the switch case. The thing that we add here, the trade-off that we make, is that we're making one big lookup table for all the handler addresses in order to get rid of this outer loop and the switch case. So the next thing we're going to do is called direct threading. This is a second optimization after indirect threading, and we're going to get rid of that table. All right, so what we're going to do here is we're going to just observe that every time we go to the table, we're going to use the opcode to index into that table. So the opcode is really an index. So the thing that direct threading does is it takes that observation and goes one step further. It says, instead of using the opcode as an index into the table, why don't we just make a pass over the bytecodes and replace each opcode with the address of its handler. We know every single opcode, because we can read them from every single instruction. We're just going to swap that byte, an opcode out, and replace it with the address of its handler. So now when I decode an instruction, I simply use jump to the opcode, because the opcode is now an address. So you get all the same benefits as indirect threading, but now you don't have this lookup table. What we added, however, is that we have to translate a program when we first read it in, and that can be done pretty quickly. But we're swapping out a 1-byte opcode for a 4-byte address, so the code is going to get bigger. If you want to do this today, you can. You can do it with a CPython interpreter, but you're going to have to compile it with GNU-C so that you can use labels as values to do this threading. Okay, so we now see the difference between native execution, decode and dispatch, and direct threaded interpretation. So if we take a look at direct threaded interpretation at a high level, what you have is a series of interpreter routines. Each interpreter routine reads from memory, so there's a data flow from the program that's in memory to the interpreter routine, the dotted line. We're then going to execute the operation for that instruction, and we're going to, at the end of that, we're going to read the next instruction, decode it, figure out what its address is of the handler, and jump to the next handler. So our control is going to be jumping between handler routines over time. If we take a look at some real programs and real interpreters, on the top we have Java, and the bottom we have Python. These are both interpreters. And I just want to show you the difference in interpreters. So at the top, the bars are broken down. I'm going to describe them from the bottom to the top. So the bottom, the red part of the bar, is the time spent in the dispatch loop. Okay. Above it is the time spent in the runtime. This is the effort that's made by the garbage collector and by other runtime data structure accesses required to implement some of the instructions. Above that is the library calls out to library routines. Above that is the operating system calls to do I/O and other things. And then above that is everything else. And so each of the programs are normalized to their total execution time. And then, so you can see the percentage or the portion of the total execution time that is that these different pieces account for. And I do the same thing for the Python interpreter at the bottom. And if you go to the programming language shootout on the web, there's the same programs are written in lots and lots of different languages. So some of these programs are not the same across Java and Python, but some of them are. And we got those from the programming language shootout online. And what you'll see in general, the general observations is that more time spent in the loop, the dispatch loop, the interpreter loop for Java than Python. And this is because Python instructions are not typed. So we can do the decode and dispatch, but when we go to implement a Python instruction, we have to go out to the VM runtime to figure out all of the types of the operands on the fly. So less time, so we have to do a lot more work for each instruction just figuring out the types of the operands. In Java and .NET, we know the types of the operands because the instruction, the opcode, tells us. So again, more time is spent in the dispatch loop in Java because less work is done for each instruction. So I can do more instructions in the same amount of time in Java than I can for Python. So Python, less time is spent in the loop of the interpreter. So what this means is if we're going to optimize the interpreter and reduce the time spent in the VM loop, we're going to impact the performance of Java programs more than we are for Python because more time is spent in the loop overall as a proportion in Java programs than in Python. So if I'm going to try to optimize the red part of the execution, since there's more red parts for Java, I'm going to have more potential for improvement than I am for Python, since for Python the red part consists of a much smaller portion of the overall execution time. Another way of looking at this is with dispatch rate. What you see here in the bars is the number of dispatches for every 100 cycles. So if you can do more dispatches, that is more work in the same amount of time, you're running faster. So I show you blue. The first bar, the bar on the left, blue, is Python, and the one on the right is Java. And again, these are both interpreters. And what you see here is that there's more cycles per dispatch for Java bytecodes because we have to go in and figure out what the types are of the operands. And this just takes time. And so the other thing that is different about Python is that each instruction, each operation does a lot of work. It can do a lot of things. Like, for example, there's built-ins for lists and tuples and strings and print. And so there's a lot of work that goes on to implement a print, whereas Java pushes that out to functions in libraries, and so the bytecode operations are much simpler. So you can get a lot more bytecode operations done in a shorter amount of time. Again, Java has a high dispatch to work ratio, and Python has a lower dispatch to work ratio. So therefore, if I'm optimizing dispatches, I'm going to do better by doing so for Java than I am for Python, since so much additional outside work has to be done for each dispatch. And we're not going to notice if we reduce the dispatch overhead as much. Just want to point out one anomaly in the data where Python actually does better. This is a program called partial sums, and this is where the implementation of partial sums in Python is built in for the power function, whereas for Java it has to call a math library, which is implemented in Java to perform the power function. So in this case, Python actually does better, but it's rare when that happens. Okay, so these are some of the interesting points made in the paper as well. They point out that there's a flat sequence layout for the operations for bytecode languages, VM instructions. This makes it really fast to manipulate, but again, it's going to be, in some cases, harder to optimize the interpreter loop for. The amount of the amount of interpreter work per the amount of progress we make in the program dictates the level of the operation. So again, let's say if you have Java instructions where you already know the type, then in order to execute that instruction, you do less work because you don't have to figure out what the types of the operands are. For the same instruction in Python, you have to do additional work to figure out what the types are. So therefore, the dispatches, the bytecode is lower level. That is, they describe finer grain operations in Java than they do in Python. Python are more coarse grained. That is, the interpreter has to do more work per bytecode. And so this level dictates the performance we're going to get if we optimize the interpreter for this dispatch. If you have programs with high dispatch to work ratios, a high dispatch rate like Java, you're going to have more of an impact on overall performance than you are with a lower dispatch rate in language like Python. So the programming languages that the paper considers are Java and this language called G4. G4 is even lower level than Java in terms of its bytecode. It has a higher dispatch rate. They have more dispatches for the same amount of work versus Java. So there's going to be more potential for us to improve the performance of G4 programs if we focus on the dispatch loop, because the dispatch loop takes a larger portion of the overall execution time, because we're doing so little work each dispatch that the cost of the dispatch loop is not amortized as much. So we're going to try to improve dispatch and for lower level languages, we're going to have more of an opportunity to get performance back. In terms of the Java JVM, there's more time outside of the interpreter loop than G4th, just like Python has even more than Java. G4th caches the topmost operand stack element in a register to make the operand stack manipulation much faster. And the paper shows some initial results for G4th that says that 16.5% of retired instructions are indirect branches, where there's only 6% for JVM. So if we're going to focus on an optimization that reduces branch misses, more benefit will come from G4th since there's more indirect branches than for JVM where there's fewer. The paper points out that the biggest problem with interpreters on performance is branch mispredictions. If the hardware cannot predict where it's jumping to, and there's a tremendous number of branches and jumps, then there's going to be a lot of mispredictions, and that's going to hurt performance significantly because we're putting bubbles in our pipeline and destroying the throughput of our processor. The deeper the pipeline, the worse the cost. And there are two sources of overhead in every dispatch loop. There is just the pure number of dispatches, and then there's the cost per dispatch. And so the paper is going to try to address both of these in combination. And the solutions that the paper puts forward are called replication and super instructions. Replication is where we're going to make a copy of the handlers so that each instruction has its own handler, has its own copy of the handler. There is dynamic replication, and this is where we're going to make a copy for every instruction that's executed. So every instruction in the program that executes is going to get its own copy of its handler, so its interpreter routine. And then we're going to concatenate each of those handlers into one long chain. If we do this, then every time we execute the same instruction again, so if we're in a loop, then we're going to jump between one handler and another, the same as we did in the last iteration of the loop. So the program is going to become more predictable. We can also do static replication. Static replication is where when we're developing the interpreter, that is, when we build the interpreter, we're going to guess at how many copies we're going to need. Notice before with dynamic, we're going to make a copy at runtime, but this is more work at runtime. But we can ensure that we're making just enough copies for each instruction in the program. Again, we're making a single copy for every instruction in the program. With static, we don't know what programs are going to execute. Static means before execution. So we don't know what programs are going to look like. So we have to guess at how many handler copies we're going to need for each instruction, each opcode. So this is only a guess. And the way we guess is we run a bunch of programs and we profile them. That is, we collect information about their execution and about the number of instructions they have, the number of copies they'll need, and then we just make a decision that we're going to have a certain number of copies for each instruction type. So in the example below, we have decided that we're going to make 2 copies of iLoad and 1 copy of iAdd. And for the program on the left, we actually have 3 iLoads and 1 iAdd. So 1 iAdd works, but 2 of the iLoads are going to have to be mapped to the same handler. And we can do all kinds of optimizations to try to guess how to do this mapping, and we can try to build as many handler copies into the runtime, but it's still a guess. But we can do it ahead of time so we don't have to introduce any runtime overhead. Once we have the different copies of the handlers, we can do the mapping using something like a greedy algorithm to try to figure out, what instructions to map to the same handler, because those handlers are going to be the ones that have poor branch behavior, so because we're not going to be able to predict, we don't know which instruction we're at. So what we want to do is we want to try to avoid that as much as possible, so we can make the cold code point to those as one example of optimization. Okay, so what the side effect of is with replication is there's a lot more executable code. The footprint of the runtime system is now much, much bigger, because instead of having one copy of each handler, we now have many, many copies of each handler. Notice that we also have the exact same number of dispatches. That is, whatever instructions execute in the program, that number of dispatches is going to happen. We're not reducing the number of dispatches. And actually, we have the same number of indirect branches. We're going to jump between handlers over and over. However, because we don't have multiple instructions, and ideally in all cases, pointing to the same handler, we know that we have branches that are much more predictable. If this particular push is always followed by an IAD, if those two handlers are linked, the branch predictor, after they execute for the first time, will get it right the next time, assuming no conflict or capacity misses in the branch predictor. So the next optimization is called super instructions. And the first thing we need to do here is step back and identify what basic blocks are. I kind of hinted at them by using the term basic block earlier, but I want to stop here and describe what basic blocks are. In particular, they're straight line code. So you're going to have a program, you're going to take a function, you're going to look at the instructions in that function, and you're going to figure out where the jumps and the branches and the calls are. And what we're going to do is we're going to build blocks of straight line code. That is code for which the only way in is through the first instruction in the block, and the only way out is out the bottom. Now, going out, you could jump to different locations. You could have a branch, you could have a jump target and a fall through target, but control only executes from the bottom of the block. And this is nice because this means that if any of these instructions execute, all of them will execute. So we can do some optimization across them to do interesting things. The other thing it gives us is this ability to make a graph out of our functions. For each function, we're able to build a control flow graph. This is a graph for which the nodes are basic blocks and the edges are how execution flows between the basic blocks. Now this is static, right? We can look at the program and we can identify the basic blocks without knowing how the program is going to execute. What the control flow graph shows are all of the possible ways that a function can execute, all possible paths. So for example, in the code on the left, if we translate the while loop into gotos to have more fine-grained control over our instructions, we get the code on the right. We now can break up this code in a way that each basic block has one way in and one way out. And we can link those basic blocks such that they're all connected based on how the program can possibly execute. So for the goto in the second basic block, we have a conditional branch. That conditional branch, if that condition is true, goes one way, and if it's false, goes another way. And we can have direct branches, unconditional branches like at the bottom, the goto, where that the output of that basic block goes to the start of basic block B4 in this example. So let's look at the algorithm and how we develop basic blocks. It's really very simple. There are 3 rules. The first one, and the goal of the rules is to find leaders. They're going to be the first instruction of a basic block. The leaders in a function are the instructions that start a basic block. So there's 3 ways to find leaders. The first one's the easiest. The first instruction of a method is a leader. Second, if we call it in the slide I call them tuples, but they're just instructions. If an instruction L is a leader, if there is an instruction that points to it, that is, there's an instruction that has a go-to to this instruction, or there's a conditional branch that has one of its edge point to this instruction. So an instruction is a leader if it is the target of a branch or a jump. And third, an instruction is a leader if it immediately follows a branch or a jump. So basic block consists of a leader and all of the following instructions up to the next leader. So if we want to do this as an example, the rules are at the top, the source code's on the left. I translate it to an intermediate representation with go-tos because it's just easier to process. And then I find the leaders. The first instruction of the method is a leader via rule 1. Instruction number 3 and instruction number 7 are leaders because of rule 2. They are targets of a branch or jump. And instruction number 5 and instruction number 10 are leaders because of rule 3. They follow a branch or a jump. You should be able to find the leaders and draw the basic blocks and their control flow graphs. So what we have to do here is put the edges between the different basic blocks that we found to the appropriate targets, and that is a control flow graph. So back to super instructions. So for super instructions in the paper, the first thing we got to do is identify the basic blocks in your program. This is a static analysis that's done to identify the straight line pieces of code. Then for each basic block, we're going to make a dispatch body. So notice before we were dispatching and invoking a handler function for every single instruction. Now what we're going to do is we're going to combine the handlers of all the instructions in a basic block into one super instruction. And what this allows us to do is remove all that dispatch code from in between those instructions within the basic block. We just have to do the dispatch at the end correctly, and that's what a super instruction is. It's a handler for each basic block. What's nice about this is that we remove dispatch overhead. We have fewer dispatches because we're going to dispatch at the basic block level instead of at the instruction level. Now we have a choice. If you have two basic blocks that are identical, you can either use the same super instruction, that's the same handler. In that case, if you have multiple blocks pointing to the same handler, the target of that handler will be less predictable because you don't know which instruction, which basic block you're coming from. Again, if you have two basic blocks and they have the same handler, when the handler executes, you don't know which basic block it's implementing. So sometimes it'll be for one, sometimes it'll be for another, which means the target of the basic block will be different for either case. If you have multiple targets, then the branch becomes less predictable. And so for simplicity, we can simply use the same super instruction for identical basic blocks, and then we lose predictability and maybe we'll have some more branch misses. However, we could combine super instructions with replication, where we make copies of handlers and link them such that we have very few of the same instruction, or in this case, basic blocks, referring to the same handler. So therefore, it makes our branches more predictable, and therefore we'll have fewer misses. So the paper does exactly that, and it shows the benefits with just replication alone, static and dynamic. It shows the benefits of using super instructions alone, static and dynamic. And then, I'll take that back. Super instructions, you just simply use the basic blocks. So super instructions alone are just static. There's no dynamic equivalent. And then when we combine replication with super instructions, you can use static replication for that combination, or you can use dynamic replication for that combination, and they show the results across all of them. In general, what they find is that the combination of replication and super instructions does the best. they find more benefit for G4th than for the JVM, and that is because G4th is a lower level language in bytecode. That means that the JVM has fewer dispatches to begin with for the same amount of work as G4th. That is, because G4th instructions are lower level then and very fast, more time proportionally in the overall execution is spent in the dispatch loop. Therefore, if we optimize a dispatch loop, we will have more of an impact on G4th, and that's what the results show. The results, in summary, show that many ICAS misses can be avoided, and they can improve performance over just regular baseline interpretation by 4.5 times for G4th and 2.7 times for the JVM. Now, if we were going to dynamically compile these programs, just to give you a feel for this, dynamically compiled G4th is 3 to 5 times faster than interpreted, and JVM code dynamically compiled is 9.5 times faster than interpreted. So they show that dynamic is better, but again, we don't. It uses more resources and grows the footprint of the interpreter quite a bit. Static does okay for G4th, but not for the JVM. You really need dynamic replication for that. And then they show that the combination of replication and super instructions does the best. What I liked about the paper was that they show these results, they experiment with these results using different hardware and branch predictors and branch target buffers, and they explain each of these different branch prediction technologies pretty well in the paper.